Remember in our past lectures that we were talking about how if we were trying to find the slope of a line, let's say a line tangent to the graph right here, we would need to have not just one point to find that slope, but 2 points to find the slope. And so let's say that this was the point, we'll call this 1, 1. So this is x is 1 and this is y is 1. If we were trying to find the slope there, we would need to kind of scoot over h units away and invent a new point, which we're going to call 1 plus h. And that means that we're going to put the 1 plus h into the function to get our y value. And what we would do is we would find the slope between those 2 points, with the end goal that we would want to move that h so that it goes closer and closer to 1. So we talked about the fact that we were finding a slope, and to find a slope you do y2, take away y1, over x2, take away x1. And in our particular case, we said that y1 wasn't just x squared, but when you plug in 1 for x, you end up getting 1 for y. So this would be a 1 here. And then what we did was we simplified all of this, and we said that we would do 1 plus h squared, which makes this, and you're subtracting 1 squared, and you're putting all of that over h because the 1's cancel in the denominator. Likewise, the 1's cancel in the numerator. Oopsie. And so you end up with slope is, and you factor out an h, 2 plus h over h. The h's can cancel, and you end up with 2 plus h. So if we end up having h be 0 so that it disappears, our answer would be that the slope of that tangent line right here at the curve would be a slope of 2. So that leaves us to something called a derivative. The definition of a derivative is that we're talking about the slope of a point the slope of a curve at a particular point. So now they're giving it a name. They're calling it the definition of derivative. And again, derivative is a slope of a curve at a particular point. So what they're doing now is they're formalizing all of this definition of derivative by now using our terms of limits to say that not only are we just going to say like, oh, we want h to disappear, but we want h to become 0. So we're taking the limit as h goes to 0 of f of x plus h minus f of x all over h. So now let's say that we were finding the same function, and we were now trying to find the slope at x is 2. And so now what we're going to do is use this definition of derivative to do that. And so in order to do that, I would say I'm going to find the limit as h goes to 0. And I'm going to do f of x plus h. So that would mean that I would have 2, which is x, plus h squared, minus f of x. So when you plug 2 into the function, 2 squared is 4. Again, that's just y2 take away y1 over x2 take away x1. And now we can see that if anytime we do x2 take away x1, we just end up with an h in the denominator, because it would be 2 plus h minus 2. And so then they would drop out. Okay, so now I'm going to finish continuing here. I have the limit as h goes to 0. I do my distributing here. Which would allow me then to cancel the 4's in the numerator and also factor out an h. And now I know if I'm trying to take limit as h goes to 0, the first thing we try to do with limits is try substitution. And indeed, if we substitute in h as 0, I get 4. So it's the same exact process we were using in the last lecture, except this time we are using a definition of derivative where now we put in the limit as h goes to 0. Let's take a look at another example. In this particular example, I'm trying to find the slope of this curve at any point x is a, and then I want to specifically find the point at x is equal to -1. So what this is doing is it's telling you to write a general formula, which is the formula for the derivative being a slope at any point, and then at the end plug in the fact that x is equal to -1. So in this case, what I have is 2 points. I have the original point being x comma 1 over x. And then the second point would be x plus h, and then 1 over x plus h. And so now I'm going to find the derivative. And the symbol we use for derivative is dy over dx. Derivative is just slope at any point. So I'm just writing a general function at this point. And I'm going to do my limit as h goes to 0 of f of x plus h minus f of x all over h. Again, you can see you get h because it's x2 take away x1. The x's would cancel. I'm now going to get a common denominator in the numerator. And so my common denominator would be x times x plus h. So I can see that the first function would need an x in the denominator. The second function would need x plus h in the denominator. So I'm going to go ahead and multiply the numerator by x plus h. Now when I go ahead and distribute my negative sign, I would get x minus h with the common denominator. I can see that my x's in the numerator cancel. Keeping in mind that this is just the numerator, so this is still being divided by h. You don't want to lose that h. It's still there though. And so then when I simplify this, I end up with my x's canceling. And so I end up with negative h over x times x plus h. But when I divide by that other h in the denominator, it's the same thing as multiplying by 1 over h, because dividing by h and multiplying by 1 over h are the same thing. And now when I substitute in h is 0, because that's what you do in a limit, you end up with -1 over x squared. That's what we call the derivative of the function. And the cool thing is that is now a slope formula for anywhere on the curve at any point. So I can take any x value and find that slope at any point. In this particular case, they asked for what was the slope at x is 1. And so at x is equal to, I think they actually asked for -1. So if they asked for -1, you would substitute in -1 for x. And that means that you would end up with a slope of -1 over negative 1 squared, which is 1. So my slope at that point is negative 1. The second thing that the problem asks for is where does the slope equal negative 1/4? You'll notice in the notes. And so in order to figure out where the slope equals negative 1/4, I would want to take my derivative formula I just found, which my derivative formula was negative 1 over x squared. And that's the slope at any point in the curve. And I'm going to set it equal to negative 1/4 to find out where that slope happens. And so when I solve, I would end up with, in cross multiplying, I would have x squared equals 4, which means x could be either positive or negative 2. Part C asks what happens to the tangent line to the curve at the point a, comma 1 over a as a changes. And I can see that my slope here would be steeper than my slope here. So as a gets to be a larger value, your slope is actually decreasing. Whereas when your a gets to be a smaller value, you can see that your slope is dramatically increasing. So again, we're talking about the derivative of a function is a slope at any point. There's a couple of ways they could express derivative of a function. They could ask you to find the derivative. They could ask you to find the instantaneous rate of change. They could ask you to find slope of a tangent line to the curve. Or they could even just ask you to differentiate, which just means to take the derivative and use the derivative formula as we see in the definition of derivative. So anytime you're asked on an exam or a quiz or anything for using the definition of derivative, this is one of the formulas that you would like to use. So this further then examples exactly what we just said. We could be talking about slope of a tangent line, rate of change, derivative, instantaneous rate of change. Those are all very similar things. There's a second formula for definition of derivative. This is a formula that people use if you would rather have 2 points rather than having your point being one being x and one being x plus h as your x values. In this particular case, they have 2 different points, one being x and one being z. So you're still doing a slope formula, y2 take away y1 over x2 take away x1. But in this particular case, what you're trying to do is make your z turn into x. You want your z to get as close to x as possible so that you'll be on top of that x point. So you can see here we have limit as z goes to x. This particular formula seems to work well when you have things like square roots or when you have rational functions, such as we have here. So again, we have a word, but it's a new word. We said that differentiate means take the derivative. So I'm going to go ahead and use this new formula where I say my derivative is x2 take away x1. So if I put z's in, I would have z over z minus 1 minus x1 over x2 take away x1. You would need to get a common denominator, so my common denominator would have to have both the x minus 1 as well as the z minus 1. So you do your little maneuver of getting common denominators. You would go ahead and distribute on the numerator, making sure that you distribute your negative in the second fraction. Oopsie. And of course, very important part of the formula is the limit as z goes to x, because we really don't want the z's at all, right? So in every step of the way, you should be putting that little limit in there, the limit as z goes to x. Sorry about that, I kind of left that out. But very important that you keep that in there because we haven't eliminated that step yet. We still are talking about that limit. So let's go ahead and do our distributing. We end up with zx minus z minus zx plus 1. And we have a denominator, which I'm not going to multiply out. I also know I'm dividing by z minus x, which is the same thing as multiplying by 1 over z minus x. We can see that the xz's cancel in the numerator. And in the numerator, I end up with negative z plus 1, which actually can kind of cancel with the denominator a little bit if I were just to take out a negative sign. So I'm going to go ahead and take out a negative in the numerator, which then makes a z minus 1. And I still have this in the numerator, 1 over z minus x here next to it. So these can actually now cancel. And now substitution works just dandy. I'm going to have negative 1 in the numerator left, and I'm going to make all the z's into x's. So I would end up with, oopsie, something went a little wacky. Please hold. Ah, yes. I have seen what I did wrong. Up here where I just did my distributing, let me show you. Right here. Negative x times negative 1 should have been positive x right here. That was my issue. So actually what I have in the numerator here, let's do some erasing. Let's walk it back. Sorry about that. Everybody makes mistakes. It happens. So now I have in the numerator on the top, I have negative z plus x and over here I have z minus x. So again, notice that diagonally the signs are opposites. So what I want to do is factor out a negative 1 up here, which would make the z positive and would make the x part of this negative because I'm factoring that negative out. And now these two things are the same diagonally. And now substitution works just ducky. So I'm going to make all my z's into x's. So I can see in the numerator I have a negative and an x left. And in my denominator, I would have x minus 1 twice. So there would be a square. Oopsie, actually in the numerator, I don't know why I put negative x. I actually only have negative 1, right? Right here, I have a negative left, and I have this 1 left. So there's a negative 1 in the numerator. Let's try another one with a square root. So we're going to find the derivative of f of x for the square root of x for x is greater than 0. And I'm going to use that same formula again just to show you how it works with 2 points. So my 2 points would be x square root of x and z square root of z. So I'm going to do limit as z goes to x of f of z, minus f of x over z minus x. As we talked about before, we can't simplify these things the way that they are, but we did talk about how we have that magical, mystical conjugate, which seems to make lots of magical things happen. So I'm going to go ahead and multiply by that conjugate in the numerator. And when I do all of my distributing in my numerator, I would end up with z minus x in the numerator. Which cancels with the denominator. So I'm just left with a 1 in the numerator, and now when I replace my z's with x's, I would have a square root of x plus a square root of x in the denominator, which would end up to be 2 square roots of x. Now that I have that, that is my slope, that's my derivative. It's my slope at any x value. So when they ask you to find the tangent line to the curve at x is 4, we need the slope at x is 4. So if I just go ahead and substitute in 4 into my slope formula, I end up with a slope of 1/4. They want the equation of the tangent line. So I need to know what point exactly is at x is 4. So when x is 4, I know that my equation was square root of x, so square root of 4 would be 2. So my tangent line would be y equals the slope times x minus x plus y. Lastly, there's lots of ways that we can show derivative. We can show derivative with f prime of x, y prime, dy over dx, df over dx. And in some rare instances, you may see d over dx of f of x, or even rarer, the last two formats. All of those things all say the same thing, which is take the derivative. Lastly, in order for a function to have a derivative, it has to be continuous there. Basically, if you don't have a point at a certain x value, then you can't have a derivative there because there'd be no point to have a slope at. So differentiability, taking a derivative, implies that the function was continuous. That's all the notes that we have for tonight. So don't forget that I have set up a Delta Math to get ready for the quiz that is on Wednesday. The quiz on Wednesday does not involve any of what we just talked about. It is basically from Chapter 2. So I will see you all on Wednesday. Hope you all have a good night and hope you had a happy President's Day.